So hello and welcome in this video on moment generating function. So in this video basically we will discuss about the moment generating function, means how we can obtain the expression of moment generating function, and the second thing which we will discuss in this video is that how we can obtain moments from the moment generating function. So first of all, let us discuss how do we obtain the moment generating function. So moment generating function, if we represent this moment generating function as of a random variable x as mxt, so here this x is a random variable, maybe it is discrete or continuous, and this t is a parameter. Okay, basically this is a parameter of our moment generating function. So this is our parameter. So this moment generating function can be obtained simply by finding the expectation of e to the power tx, right? So when you are going to calculate the expectation, so the calculation of expectation depends on the type of the random variable. So here, if your random variable is discrete, if this x is a discrete random variable, then expectation of e to the power tx is simply obtained as e to the power tx multiplied by px, or you can also write it as txi multiplied by pxi. Here xi is this xi is the value of the random variable. Okay, so this is the values of the random variable, and this pxi is the probabilities, or you can say the corresponding probability. Okay, so this is how we can obtain this moment generating function for the discrete random variable. Now if this x is the continuous random variable and this continuous random variable x has this fx, which is the PDF of this random variable, then expectation of this e to the power tx can be obtained by integrating the product of e to the power tx and fx with respect to x. And here we can consider the general limits, which are minus infinity to infinity. However, the limits totally depends on the expression of fx. So this is how we can obtain our moment generating function. Now the important thing is, before we proceed towards the problems or examples, let me discuss how do we obtain the moments from this moment generating function. Okay, so for this we know that the expression or the expansion of e to the power x is 1 plus x square over factorial 2 plus x cube over factorial 3 and so on. So using this expression we can easily write the expression of e to the power tx as, now what we have to do, we have to replace this x by this tx. So this is tx plus tx whole square over factorial 2 plus tx whole cube over factorial 3 plus so on. So this is how we have this expansion of e to the power tx. Now the moment generating function is defined as the expectation of e to the power tx. Now using the expansion of e to the power tx, this expansion, we can write this as expectation of 1 plus tx plus tx whole square over factorial 2 plus tx whole cube over factorial 3 plus so on. Okay. Now we know that we can write this as expectation of 1 plus t times, because this t is the parameter and x is the random variable, so this can be written as t times expectation of x plus t square over factorial 2 expectation of x square plus t cube over factorial 3 expectation of x cube and so on. Now if you look at this expression, so here we can notice that the coefficient, or it will be good if we mark this as our expression 1. So coefficient of t in 1, okay, so this is t. Now the coefficient of this t is our expectation of x, okay, so this is our coefficient of t. So this is our expectation of x, and this will be our first moment about 0, or you can say the origin. Now next we have this coefficient of t square over factorial 2, again in expression 1, and you can easily notice that here the coefficient is expectation of x square, right? So this is our expectation of x square, which is our second movement about 0, okay. And similarly we can continue with this, and we can collecting the coefficient of t cube over factorial 3, again same in expression 1. So this is t cube over 3, and the coefficient is e to expectation of x cube, and continue in this manner. We have that coefficient of t to the power 4 over 4 factorial in 1. So we can easily write this as, because the coefficient of t cube over factorial 3 is expectation of x cube, okay. So this is our expectation of x cube, and so which is our third movement, okay. So this is our third movement about 0, and surely this will be expectation of x to the power 4, which is our fourth movement about origin. So this is the first procedure to obtain the moments once we are having the expression of our moment generating function. Here what we are doing, we are just collecting the coefficient. The important thing is this expectation of x square, or the second moment about 0, is not the coefficient of t square, rather it is the coefficient of t square over factorial 2. And similarly this expectation of x cube is not the coefficient of t cube, but the coefficient of t cube over factorial 3. So this will be very important, that we have to remember that this factorial 2, factorial 3 and factorial 4, when we are calculating or when we are finding the second, third and fourth moment respectively. So this is the first procedure by which we can obtain the moments from our moment generating function. Now another or the second method which we can use to determine the moments from the moment generating function. So again, as we written here this expression 1, now what we will do, we differentiate this expression 1, or we can write this, because this expectation of e to the power tx is the moment generating function. So for simplicity I will write this as m t. The second procedure or the second method by which we can obtain moments from this moment generating function is we start differentiating this moment generating function. Again, this expression which is written here as expression number 1. So when you differentiate this with respect to t, so first one is expectation of 1, which is 1 itself, because we know that the coefficient the expectation of the constant is the constant itself. So when you differentiate this 1 with respect to t, so it should be a 0 plus, now because we are performing this differentiation with respect to t, so here the derivative of t with respect to t will be 1. So this will be expectation of x plus the derivative of t square is 2t upon factorial 2, and we are having expectation of x square, and the derivative of t cube is 3t square over factorial 3 expectation of x cube, and so on. So what we are doing here, we are just differentiating our moment generating function with respect to t. Now we will find out the value of this first order derivative at t is equals to 0. So means what you are doing, you are putting t is equals to 0 in this expression. Okay. So when you are putting t is equals to 0, so it is very much clear that after the first term, because starting from here, every term involve this t. Here you can see that it is t square, and the next term will contain t cube, and so on. So when you are putting this t is equals to 0, so this entire expression will become 0 except this, because here no t is involved. So this will be expectation of x, which is of course, as you can see here, which is our first moment about origin. Okay, so this is our first moment about 0. Now continue in this manner. If you differentiate again this expression, means you are finding the second order derivative, so that will be coming out as, so in order to obtain this second order derivative, what we will do, we just differentiate this dm over dt again with respect to t. So now you can see that it is 0 already, so the derivative of 0 is 0 itself, and again this expectation of x is constant because we are performing the derivative with respect to t. So this is not a function of t, so this can be considered as constant here. So this is 0. Now here you can see that we are having t, and this factorial 2 is 2, and both 2 upon 2 will be cancelled out, and the derivative of this t will be 1. So we are having here this as expectation of x square plus we will have 6t upon factorial 3 expectation of x cube, and so on. Now if you find out the value of this second order derivative at this t is equals to 0, so again you can see that from here onwards we are having the terms containing t. Okay, so when you are putting this t is equals to 0, the entire expression after this expectation of x square will be 0. So we left with the expectation of x square. So this will be the second moment about 0. Okay, so this is our second moment about 0, and similarly you can obtain the third moment by differentiating your moment generating function and putting here this t is equals to 0, and this will give you expectation of x cube, which is your third moment. And lastly, if you differentiate this moment generating function 4 times with respect to t and putting this t is equals to 0, so this is coming out as expectation of x to the power 4. So this is your third moment, and here you are having your fourth moment about origin. So this is how we can obtain. You can use any of the method, but in some cases only one is applicable. It depends on the expression of the moment generating function. So as you can see that we are having two methods. First one is by collecting the coefficients, different coefficients, and the second method is we have to differentiate the moment generating function. So now here it will be good if we use certain examples to understand that how we can obtain the moment generating function. So let us first discuss this example. So here we are given that x is a discrete random variable having the mass function with the probability mass function as probability of x is equals to r as kr square, and the values of r is given as 0, 1, 2, 3. So here we have to find the moment generating function. Okay, we are given a discrete random variable along with its mass function, and we have to determine this moment generating function for this random variable. So here let us begin with the solution. So first of all, what we will do, we just make the distribution here. Okay, so distribution means we are having the random variables, values of the random variables, and the corresponding probability. So we are given 4 values, and the values are 0, 1, 2 and 3. Now when you are putting here the first value, which is 0, so that should be k into 0 whole square, which will be 0. Okay, so this is 0. Similarly, when you are putting r is equals to 1 here, okay, when you are putting r is equals to 1, so that should be k into 1 whole square, so which is k, so this is k here, and using r is equals to 2 here, you will obtain this as 4k and 9k. Now before we find out the moment generating function, first of all we will determine the value of k. So here we will use the property that the sum of all the probabilities will be 1. So from here you will obtain this as 0 plus k plus 4k plus 9k is equals to 1, which gives you 14k is equals to 1, and subsequently we obtain the value of k as 14. So this is the value of k, means the unknown involved here. Now once we are having this value, we are having a numerical value of the probabilities for each of the possible values of our random variable. Now next we will determine the moment generating function. So as we discuss, the moment generating function is expectation of e to the power tx, and this, because we are dealing with the discrete random variable, so this will be e to the power tx multiplied by px. So our first value of the random variable is 0. So that should be e to the power, when you are putting x is equals to 0. So this will be e to the power 0 multiplied by the probability of x is equals to 0. This, which is 0. So this will be multiplied by 0 plus the next value of our random variable x is 1. So this will be e to the power t, because when you are putting x is equals to 1, so this will be e to the power t multiplied by the corresponding probability of this x is equals to 1, which is k, or you can say that 1 by 14, because the value of k is 1 by 14, plus next value of x is 2. So this will be e to the power 2t multiplied by the corresponding probability. Here you can see that the probability is 4k, means 4 upon 14. So this will be 4 upon 14, and the last value of x is 3. So this will be e to the power 3t multiplied by the corresponding probability, which is 9k, or you can say that it is 9 by 14. So you can take this 1 by 14 outside, and because this is this will become 0, okay, this will be 0, because e to the power 0 is 1, and when you multiply this by 0, so this will be 0. So this will be e to the power t, because 1 by 14 is outside, we are starting from here, and the next term is e to the power 2t, and 1 by 14 is outside, so this is 4 times e to the power 2t plus 9 times e to the power 3t. So this is our moment generating function. Now we can obtain, so this is the expression, or this is the procedure by which we can obtain the moment generating function. Now next we will find out the moments, or you can say that suppose we have to find out the mean, and when I am saying the mean, it means expectation of x, or the first moment about 0, and the variance, okay, and variance. So variance, for variance we know that we have to find out expectation of x square also, because the formula of variance is expectation of x square minus expectation of x whole square. So this expectation of x square is our second moment. Second moment about 0, okay. So we obtain first and second moment using this moment generating function. So as we discuss, we will in this particular example, I will use both the procedures to obtain our moments from this moment generating function, means by collecting the coefficients as well as by performing the differentiation of our moment generating function. So let us start with the first method, okay. So first method means by collecting the coefficients. You can use either method. So here I am just using the first method, means by collecting the coefficients of difference power of t. So for that we have to expand this moment generating function, means so from here if I represent this by mt, so this mt can be written as 1 by 14, and this e to the power t, so using the expansion of e to the power t, we can write this as 1 plus t square over factorial 2 and so on, because we need only first and second movement. That's why I am just expand this up to t square, and similarly we can expand our e to the power 2t. So this will be 1 plus 2t plus 2t whole square over factorial 2 and so on. And lastly we have this 9 times e to the power 3t. So when you are expanding this e to the power 3t, so this will be 1 plus 3t plus 3t whole square over factorial 2 and so on. Okay. So now because in order to obtain, we know that okay, so let's first write this. If you are collecting the like terms, means first one is constant, so here it is 1, in the next bracket it is 4, and in the last bracket it is 9 multiplied by 1, so it is 9. So this will be our constant term. Next we will consider the coefficient of t. So here it is 1. Now here the coefficient of t is 2, and in the last expression, in fact this is not 2, if you are considering this 4 also, so this will be 4 into 2, so this is 8, and similarly when you multiply this 9 with 3t, so this is 27, and these three terms are the coefficient of t in different brackets. Now next we will have the coefficient of t square. So from in fact the coefficient of t square over factorial 2. So this can be written as, here in the first bracket it is 1, and in the next bracket, because you are collecting the coefficient of t square over factorial 2, so this term can be written as 4 times, because you are performing the square, so it is 4 times t square over factorial 2. This term can be written like this. So when you multiply this 4 with this term, so it is 4 into 4, which is 16, and similarly here you are having the square of 3, which is 9, and 9 when you multiply this by 9, so this is coming out 81, and this is the coefficient of t square over factorial 2, and we have some higher powers of t. Now we know that the first moment or the expectation of x is the coefficient of t, and coefficient of t means this term. Okay, so this is 27 plus 8 plus 1, so this will be 36. Okay, and similarly the expectation of x square is the coefficient of t square over factorial 2, so this will be 81 plus 16 plus 1. In fact this is 1 by 14 outside, so this can be written as 36 by 14, so you can write this as 18 upon 7, and similarly this will be coming out as 96 by 14, means when you are adding this 81 plus 16 plus 1, so it is coming out 96, and we are having 1 by 14 outside, so this will be 96 upon 14, and this will give us the expectation of x square, or the second moment about origin, as 48 by 7. So the expectation of x, or the first moment about origin, is our mean. So mean is 18 by 7, but in the question we have also need to find out the variance, and we know that the variance of this random variable is expectation of x square minus expectation of x whole square. So this is 48 upon 7 minus 18 upon 7 whole square, and this will give us the variance as 12 over 49. So this is how we can obtain our variance here. So this is by the first procedure, by collecting the coefficient. Okay. Now let us continue with this problem, and we will find out the moments using the second method. Okay. So here we are finding, or we are using the second method, and second method means we will differentiate our moment generating function. Okay. So our moment generating function is, we have already obtained our moment generating function. So this is 1 by 14, and we are having e to the power t plus 4 times e to the power 2t plus 9 times e to the power 3t. Now as we discussed earlier, that in order to obtain our first moment, what we have to do, we have to differentiate this moment generating function with respect to t. Okay, so first we are differentiating this. So this is 1 by 14. Now the derivative of e to the power t with respect to t is e to the power t plus the derivative of e to the power 2t is 2 times e to the power 2t. So we will have 8 times e to the power 2t plus we are having 27 e to the power 3t. Okay. Now this is the first order derivative of our moment generating function. So when you are finding the value of this the first order derivative at t is equals to 0, so that will be 1 by 14 is as it is. So this will be e to the power 0. So here we are having 1. Again this will be e to the power 0. So here we are having 8 plus 27. So this will be coming out as 36 upon 14, or you can write this as 18 upon 7. So this is our expectation of x, or you can say the mean or the first moment about origin. So this value is same as we obtained previously. And next, in order to obtain the second moment or the expectation of x square, first we obtain the second order derivative of our moment generating function. So this will be 1 by 14 e to the power t. What we are doing, we are just differentiating this expression because this is the first order derivative. So if we are differentiating it again with respect to t, so we will obtain our second order derivative. So this will be e to the power t. Next we are having 16 e to the power 2t plus we will having 81 e to the power 3t. So when you are obtaining the value of this at t is equals to 0, so this will be coming out as 1 by 14, and here you will have 1 plus 16 plus 81. So this is coming out as 96 upon 14, or you can say 48 by 7. So as you can see that from both the procedures we are obtaining the same values of our first moment and second moment, and using this we can again obtain the variance, which is again coming out same. So this is how we can obtain the moments from moment generating function. But yes, we are having certain limitations. Sometimes it is not possible to determine moments from the moment generating function. So in this example we have obtained the moment generating function for the discrete random variable. Now in the next example we will see how we can obtain the moment generating function for the continuous random variable. So again here we are provided with a continuous random variable. So this time x is a continuous random variable with PDF which is defined as fx as x when this x lies between 0 and 1, and this is 2 minus x when this x lies between 1 and 2, and it is 0 for all values greater than equals to 2. So we have to find out, we have to find the moment generating function. So again, let us begin with the solution. So we know that in order to obtain the moment generating function, or this mt, or you can say that mxt, we have to find out the expectation of e to the power tx. And this expectation of tx, because we are dealing with the with this continuous random variable with this PDF defining like this, so this will be minus, I am just going by the definition first, so this will be e to the power tx fx dx. This is how we define this. Now if you are looking for the definition of fx, so this fx is defined only for those value for the values greater than equals to 0, right? And even in that range, it is having some different intervals, and where it has some different values. So in the interval 0 to 1 it is x, and in the interval 1 to 2 it is defined like 2 minus x, and for all other values, means the values greater than equals to 2, it is 0. So using this we modify our limits. So the first interval where our function is defined is 0 to 1. So our first interval is 0 to 1, and here we are having e to the power tx, and fx is our x. So this can be written as x time e to the power tx, or e to the power tx into x dx, plus next we are having 1 to 2, and it is here we are having fx defined as 2 minus x, and of course we are having e to the power tx dx, plus for the values greater than equals to 2, the function is 0, so there is no use to perform this integral. So we have to deal with only these two integrals in order to obtain our moment generating function. So here, as you can see, that we are having the product of two functions, so we have to perform our integration by parts. So this will be, if you consider this as your first function and this is your second function, so we keep our first function as it is. Now this should be multiplied by the integral of the second, so that will be e to the power tx over t minus whole integration, and what we are having inside this integration. So here we are having the derivative of x with respect to x, so this is 1, and the integral of e to the power tx with respect to x, so this will be e to the power tx over t, and yet we have to perform the integral with respect to x. Plus, now here what we are doing, we are just considering this 2 minus x as the first function, and e to the power tx as our second function. So this, and again we are using integration by parts. So this will be first function, means 2 minus x as it is, multiplied by the integral of the second function, which is e to the power tx over t, minus the derivative of the first function. So here you can see that it is minus 1, so that will make this minus plus, we are having this whole integral, and so inside this integral sign we are having the differentiation of the first function, which is minus 1, multiplied by the integral of the second, so which is e to the power tx over t. Now the limits are 1 to 2. Now again we have to perform this integral. So this will be remain as it is, minus when you are performing this integral, so this will be coming out as e to the power tx over t square, and the limits are 0 to 1 plus the first term here also remains same because we have nothing to do with it, plus now again you are performing the integral with respect to x, so this will be e to the power tx over t square, and limits are 1 to 2. So now when you are evaluating the limits, so first we will obtain the expression at the upper limit, means at x is equals to 1. So this is when you are putting x is equals to 1, so this is 1, and here we are having e to the power t over t minus we are having e to the power t over t square minus the expression at the lower limit. So when you are putting x is equals to 0 here, so this will be 0, and this will become minus 1 over t square. Okay, so this is the first bracket, and now for the second bracket, when you are putting x is equals to 2, so this will be 2 minus 2, so that will be 0, and here we are having e to the power 2t over t square minus now the expression at the lower limit, so that will be e to the power t over t minus e to the power t over t square. So this is what we are having here. Now next you can see that by cancelling or by collecting or combining the like terms, so here you can see that we are having this e to the power t over t square as negative, and here also we are having this e to the power t over t square as with negative sign. So these two terms will be combined together, and we are also having this e to the power t over t, and so this is with plus sign. Okay, so this e to the power t over t is with plus sign, and this e to the power t over t with minus sign. So this will be cancelled out. So we are having e to the power 2t over t square minus 2 times e to the power t over t square, and we are having plus 1 by t square. So this is these are the terms which we are having here, and you can simplify this as e to the power 2t minus 2 e to the power t plus 1 over t square, or you can also write it as e to the power 2t sorry, this is not e to the power 2t, this will be e to the power e to the power t minus 1 whole square over t square. So this is our moment generating function. Okay, so this is our moment generating function for this continuous random variable. So this is how we can obtain our moment generating function for the continuous random variable. Okay, and simply in both the cases we have to find out only the expectation of e to the power tx. Okay, e to the power tx. So this will be our moment generating function, and this calculation of expectation is totally depends on the type of the random variable with which we are dealing. Okay, so that's all in this video.